Welcome to a lesson with Dr. Powell. This video is a continuation of the last one, where we're just setting ourselves up, thinking about this matrix here, and we're going to be looking for invariant subspaces of R3 with respect to the action of A, okay, thought of as a scalar X. Right here, so we're looking at polynomial scalars in X, and we're looking for an invariant subspaces. Okay, so here's a few notes. All right. Right here in the procedure that we're talking about, we're going to be running column operations until until it looks like row operations and maybe some column switches if we want to could take us to a diagonal matrix. So row operations plus column switches. Now, take a look at this particular example right here. And okay, so this is where we're starting, right? Because this is this matrix, xi minus a. So this is where we start. And you think, okay, well, can't we just do it with row operations already right now? Well, if you tried it just a little bit, you notice you get to this point. And why could you not? Because remember what we're doing with row operations. We want these row operations to be isomorphisms of Rx modules. So meaning that when we do scalars, we can never divide by anything. So think about what we would do here after we do one airdrop, multiplying this by x and adding up there. We get to this point, and we want to do row operations on this. I mean, how do you fiddle with this to make one of these zeros? I mean, these don't share any common factors at all. And I mean, you could do some rescaling perhaps in this particular case, but see, yeah, I mean, but they don't share any common factors. So it's not like you can multiply by a multiple of this and be equal to that in an airdropping type scenario. And then by rescaling, the problem with rescaling here, you might mess up. You might get more factors in there that we didn't really want to where we're going. Kind of what we're doing is we're remembering that this guy right here is equal to 0, and we might be adding some extra information that's not minimal by rescaling rows. So ideally, we just like to be airdropping the whole time as we move along here, so we can stick with finding things that are minimal. So row operations don't quite work here in this case as we're looking at this. If we only did row operations. So there will be some column operations, but in general, we don't really have to worry about that too much. We're just going to do column operations until it's extremely clear to us that that row operations would finish us off. So that's really it here. This is just an extra note to that end. Okay, so let's actually proceed. In fact, we're only going to be doing looks like one column operation, then we stop. Because, okay, so if we multiply this column by x minus 2, and then we add it over to this one, we end up getting this. Now, notice this one here, we could airdrop this way. Oh, that's great with that 0, 0 right there, because that would look, and then just by rearranging columns, and I mean, it looks like, or even, yeah, or even rows at that point, we'd be done with a diagonal matrix. So that's awesome. So this is where we're going to stop. I'm going to stop where we're sure that rows would finish us off, so that to get the diagonal matrix, we could use the column operations, this guy, and then row operations as a map on this side, but we don't have to worry about those because for what we're doing, because really what we're interested in is we're interested in the range or the output of this matrix here, but we want to look at it in a nice way. If we put row operations, it would change that range. We actually want to keep the same range, so we just do the column operations up to that point. All right. Because if we mod out, now what does mod out mean? It means to make things equal to 0 that we would like to be 0. So we want these representations to be the same. So we'd like this to be 0. So that's what we're modding out by. Now, if we want this matrix to be 0, then we're assuming that its columns are 0, its outputs are 0. And this doesn't change the range of those, like the linear combinations made with those. We're still in the same output thing, especially since C is this is a isomorphism with Rx modules. Okay. All right. So let's take a look. So that's step number 1, is just to do column operations up to that point. And we're on our way to try to find these invariant subspaces. Step number 2 is to look at these columns that we have arrived at and factor out anything that's a common factor. Okay, so we can do that this way, factor out anything that's common. There's not here, it's just 1. Here, x minus 1, x squared minus 2x plus 1, which is really just x minus 1 quantity squared. So we get these 3 things. Notice these 3, you can call them vectors if you want, or tuples, that we get in columns. Those are going to be important to us as we go forward from this. We'll end this video here, and we'll pick up with the next one. Thanks for watching.